Greetings, everyone. Welcome to the 221st session of the online Optom Learning Series, OOLS. And for today's session, we have with us Professor Mark Willcox. Professor Mark is a professor and a research director at the School of Optometry and Vision Science at the University of New South Wales in Sydney, Australia. He also spends time as an adjunct professor at the School of Optometry and Vision Science, University of Waterloo, Canada. Primarily, he is a medical microbiologist and has a vast experience in the areas of infections of medical devices. He runs his own lab at the university, which focuses on the development of novel antimicrobials that have the application as antibiotics as well as disinfectants. And with all that experience in the world of microbiology and working in the lab, he has developed novel products as well with a variety of purposes, which includes coating of medical devices to reduce the associated infections and things like that. He also holds a couple of fellowships from prestigious organizations. And with that vast experience, he's going to talk us about microbial keratitis, the antibiotic therapy, and how this can help us into the research as well as clinical practice. So welcome, Prof, onto our platform. And thank you so much for spending your Sunday afternoon, evening with us. And let me just leave the screen time to you, please.
Thanks very much for the introduction. And hello, everybody. Thanks for joining me today. So, yes, I'm going to talk today about microbial keratitis, antibiotic therapy, or more about resistance of the microbes to antibiotic therapy, and our development of new antimicrobial contact lenses. So, a few disclosures, conflicts of interest. I receive money from some ophthalmic companies and also some companies that make disinfectants and antibiotics. So I'll start by going through the incidence of contact lens-induced microbial keratitis, and the latest data is still actually from 2008, so about 15 years ago or so, I guess now, from an Australian study that was conducted by Fiona Stapleton in Sydney and around Australia, and they were looking at the incidence of contact lens-induced microbial keratitis. So as many other studies have shown, that the incidence is usually lowest with rigid gas permeable lenses worn on a daily wear schedule, with an incidence of about 1.2 per 10,000 wearers per year. Daily disposable soft lenses have about roughly the same incidence of 2 per 10,000 contact lens wearers per year, as does daily wear. As with all other studies, if you sleep in lenses, you increase the risk of getting microbial keratitis, and it increases it by about 10 times. So you go up to about 20 per 10,000 per year. At that stage, there wasn't any daily disposable silicone hydrogel lenses in the market, and we still don't know what the incidence of microbial keratitis is for those. But they did do daily wear, and they found that actually that had slightly increased compared to daily wear of soft lenses, as you can see. And also extended wear, of course, was still high at about 25 per 10,000. So if you wore any type of contact lenses on any wear schedule, overall, the risk was about 4 people per 10,000 contact lens wearers per year would develop microbial keratitis. Perhaps another way of looking at this is to see how many of those would lose significant levels of vision loss, so greater than 2 lines of vision loss. And they found that there was no vision loss if you wore daily disposable HEMA lenses, or indeed the rigid gas permeable. There was a slight amount of vision loss if you wore daily wear lenses, and that again increased by 10 times if you wore those HEMA lenses on an extended wear schedule. Similarly, relatively low levels for daily wear of silicone hydrogel, but also that increased if you wore on extended wear, and overall about 0.6 per 10,000 wearers would lose greater than 2 lines of vision loss per year because of microbial keratitis. So roughly around the world each year, there's probably something like 3 million cases of keratitis around the world based on these figures. Many studies have also looked at the risk factors for microbial keratitis with contact lens wearers. Most studies have looked at daily wear or extended wear. There's a few with daily disposable wear. With daily wear, if you're a male, you're more likely to get microbial keratitis with contact lens wearers than a female, most commonly. If your hygiene with daily wear isn't good, so you use older versions of multi-purpose disinfecting solutions, or you don't rub and rinse your lenses before and after you put them into your contact lens cases, or you don't clean the lens case, and I'll come back to that when we think about how to reduce the incidence of microbial keratitis. Those are risk factors, as was diabetes and smoking. And in the extended wear, male gender, as I said, and things like the longer duration of extended wear. So in other words, the more commonly you slept in lenses, the more risky it was. And also things like warm climate. And I'll come back to these risk factors when I come back to how we might reduce the incidence of contact lens microbial keratitis later on in the talk. Then more recently, Dr. Nagaraju Konda from, at that time he was at the LV Prasad Eye Institute in India. He's now at Hyderabad University and doing his PhD with me. We looked at the risk factors of contact lens microbial keratitis in India. And again, we found twice you're more than 2 times likely to get microbial keratitis if you wear lenses overnight. Interestingly, in this study, the longer you wore lenses, so if you'd worn lenses for greater than 2 years, you were less likely to develop microbial keratitis. Certainly, if you wore lenses that were replaced yearly rather than either monthly or bi-weekly, you were about twice as likely to get microbial keratitis. And then interestingly, if you were a high myope or a hypermetrope, you were less likely to get microbial keratitis compared to those people who had what was considered low myopia, so less than -6. And also occupations had effect as well. So we used students here as a referral. And we were probably expecting that these, everything else might be below or might reduce the risk of keratitis. But in fact, professional workers, so people who worked in offices, basically in Hyderabad, were actually more likely to get microbial keratitis. And that held up, as you can see in the multivariate analysis. We also looked at risk factors associated with vision loss. And as I mentioned, if I just go back a slide, with high myopia, you're less likely to get microbial keratitis. But if you do get it, you're actually about 3 times more likely to lose some vision, as you can see here. So the odds ratio is about 3.5. And we also showed that measures of severity of microbial keratitis also, not surprisingly, were associated with more risk of losing vision loss, vision loss. Well, I'm going to turn now onto the bugs that cause this disease and concentrate really on Pseudomonas aeruginosa. So it's the most commonly isolated bacteria, microbe in general, from contact lens-induced microbial keratitis. It's at least 70% of all the isolates are Pseudomonas aeruginosa, and in some studies, for example, those recent ones in Europe, at least 90% of isolates are Pseudomonas aeruginosa. So it's by far the commonest cause of this disease. This is a transmission electron micrograph of Pseudomonas. You can see it's got a sort of a fuzzy coat. These are little hairs on it that it uses to swim around. And this is a scanning electron micrograph of the bugs as well here. So with Pseudomonas aeruginosa, we can categorize them into different genetic types, and we call them sequence types or ST types. ST. And I want to concentrate just for a moment on one of those, which is 1203. Now, this sequence type is a way of showing that isolates are genetically related if there's an outbreak or even around the world, and you can track the movement of bacteria around the world by looking at these sequence types. This sequence type, 1203, was first reported from an ocular infection in India. And at that stage, the first time it was reported, it had caused post-operative endophthalmitis. It was very difficult to treat because it was highly resistant to most of the types of antibiotics that would be used to try and treat this disease, as you can see here. So resistant to cephalosporins, resistant to fluoroquinolones, resistant to aminoglycosides, and resistant also to different combinations of antibiotics that try and overcome different forms of how they become resistant. And so they looked at, in this study, at how these had become resistant, and so they'd acquired genes. So they acquired a new extended spectrum beta-lactamase. So that indicates it's an enzyme that destroys the cell walls of bacteria. That destroys beta-lactams, which in turn destroy the cell walls of bacteria. So it prevents them from destroying cell walls of bacteria. And it had also got other beta-lactams. BLA stands for beta-lactam genes. AAC stands for aminoglycoside genes, sulfonamides, tetracycline, etc. It got many genes that allowed it to become resistant to all these different antibiotics. Not only that, it had also acquired or had 12 efflux pumps. So efflux pumps make bacteria resistant to antibiotics because as soon as bacteria enter into the cell, these efflux pumps immediately pump out the antibiotics. So they never get the chance to interact with, in the case of fluoroquinolones, DNA, or in the case of gentamicin and tobramycin, the protein manufacturing machinery. So that makes them resistant. Interestingly, this bacteria also two CRISPR-like sequences. So you may have heard of CRISPR-Cas. It's now used as a potential way of treating human diseases, but originally it was found in bacteria, and it's kind of like a bacterial immune response. So it provides the bacteria a genetic memory that helps them detect if they're going to be infected by bacterial viruses, which are called bacteriophages. So they make sequences in this Casper-like region that basically allows them to memorize that they've been infected by a particular virus, and if the virus tries to infect them again, they can easily destroy the virus. So that's also important because these days, because of the developing resistance to antibiotics, bacteriophages are also being used to try and treat bacteria. But of course, if they get lots of these CRISPR sequences, they'll also be resistant to bacteriophages. This particular sequence type that was causing this disease in the eye had also got many different forms of toxins and virulence factors. So something like elastase B, which helps to degrade the stroma in the eye as well. So it was really difficult to treat. It was well armed with virulence factors, well armed with machinery that would make it resistant to antibiotics. Fortunately, it was sensitive to 3 antibiotics, as you can see here. So, for example, carbapenems and the polymyxin called colistin. So it could be treated with one of these 3 antibiotics. You may have heard over the last year that there's been a major outbreak of Pseudomonas infection, in particular keratitis, in the United States. And this again was caused by this sequence type 1203. And so people have looked at this strain and done genetic analysis, whether it's the same as the older sequence type or whether it's gained more resistance and more virulence genes. So it's in fact gained a new type of beta-lactamase called a metallo-beta-lactamase, and called the Verona integron-mediated metallo-beta-lactamase. And indeed, when they looked at whether this was susceptible, these strains that were causing the keratitis outbreak, they found that unlike the previous ST1203 isolates, which, as I said, was sensitive to these 3 antibacterials down the bottom here, the new strains had gained resistance to those 3 antimicrobials. So that was making it extremely difficult and almost impossible to treat because they were basically resistant to all the antibiotics that were thrown at it. Again, analysis had shown that, as I said, it had gained some more resistance genes, and this particular sequence type had never been reported in the United States, where this outbreak was occurring prior to the outbreak occurring in this year. Up to about May, which is the latest that the CDC have published on, because the issue has died down now, 81 patients had been infected in 18 states in the United States. The outbreak was associated with most commonly corneal infections, so keratitis, but also infection of the lungs, of the urine, of other non-sterile sites, and indeed had got into the blood of 2 patients. And very worryingly, 4 patients died of this disease because it was almost impossible to be treated because of the resistance. There were 4 reports of enucleation of the eye that was infected because the infection was so difficult again to treat, and 14 reports of vision loss. Epidemiology evidence suggested that this was caused by contamination of artificial tears that had been put into the eye, being put into the eyes because of things like dry eye. And so the CDC and the FDA in the States recommended that patients stop using these particular types of probably contaminated eye drops. And that meant that actually, in the end, the infections died out, and there wasn't any evidence of infections from a case to another person. It was because of all the cases had been using these eye drops. But as I said, very worryingly, and I think perhaps a portent for the future, is the fact that keratitis or eye infections can lead to death because they're extremely difficult to treat if they're resistant to antibiotics, like these particular strains were. Fortunately, there was one new antibiotic that they were susceptible to, and it's another beta-lactam antibiotic. This is kind of what you look for. This is the beta-lactam structure. So it's a beta-lactam antibiotic which had had new groups put on it to make it enter the cells slightly differently than normal. It was also slightly sensitive to a combination of antibiotics, but unknown whether this range was actually a useful range when treated, when being put into the eye. And I mentioned bacteriophages, these viruses that kill bacteria before, and these were also being considered as therapy because it was so difficult to treat, and they're used in life-threatening situations. So they'd have to be bacteriophages that the bacteria hadn't seen before, because they would have these CRISPR sequences in, which make them resistant to bacteriophages. But you can commonly find bacteriophages and isolate them from places like sewage, and use them, new bacteriophages, to hopefully kill the bacteria. And this is what one of those little viruses looks like that attacks bacteria. This is, as I said, this particular antibiotic is the one that it was sensitive to, and so was used to treat it. But rather unfortunately, resistance to this is also now increasing, and these bacteria become resistant to this new antibiotic again because of the production of these enzymes called beta-lactamases, which destroy this because it's a beta-lactam. Also, bacteria mutate themselves so that the beta-lactam can't get into the cells as well. They gain the use of efflux pumps, so they push out the antibiotic to become resistant, and they can also modify the target site of the antibiotic. So unfortunately, these strains were becoming resistant to kind of the last antibiotic which was available for them to be treated with, which is again extremely worrying. But as I said, this outbreak seems to have fortunately died out because people stopped using those contaminated solutions, and there was no evidence that people were getting contaminated from a patient that had the disease. So if we look at antibiotic susceptibility from around the world, fortunately where I am in Australia, we're in a fortunate position that antibiotic resistance of ocular isolates is still generally low, and so we've got a high susceptibility of ocular isolates to something like ciprofloxacin, gentamicin, and ceftazidime, which are commonly used to treat microbial keratitis. But things aren't as good in other areas of the world, and just as an example, in India, susceptibility to ciprofloxacin is below 50%. So in other words, half the isolates are resistant to ciprofloxacin. About half are also resistant to ceftazidime and cephalosporin, and about, what's that, 35% of isolates are resistant to gentamicin. So these make it difficult, again, to treat. And even though we can add lots of antibiotics to the eye because we can topically treat these things, only about possibly 5% of those antibiotics actually enter into the cornea, and so the bacteria get exposed to them. And also the amount that goes in through the cornea onto the bacteria is often well below the minimum inhibitory concentration needed to kill the bacteria that are infecting the cornea. So we've been studying this development of resistance in other strains of Pseudomonas as well. And so we've been looking, I'll just show you one of the things that we looked at, which was another sequence type. In this case was a sequence type called 308, which we'd isolated from infections, microbial keratitis in India. We'd isolated strains in 1997, and then another group of strains in 2008. And we wanted to see how these had basically changed over those 20 years. So this group of strains that you can see here in this sequence type were resistant to fluoroquinolone, so R meaning resistant, but highly resistant to aminoglycosides. Strains were sporadically resistant to some of the beta-lactams, as you can see here. And I means an intermediate resistant, meaning you need quite a lot of antibiotic to actually treat the disease. And they were generally either sensitive or of intermediate resistance to a polypeptide like polymyxin B. The 2008 isolates had somewhat changed. So if we look at fluoroquinolone resistance, we can see, for example, if we compare the strain PA33, which had a minimum inhibitory concentration of 128 micrograms per mil in 1997, strains isolated in 2018 had 10 times the inhibitory concentration of 1,280, if not much greater than that, in fact. So they had become much more resistant to fluoroquinolones. And again, even with levofloxacin, again, they'd increased by at least 10 times. So becoming effectively impossible to treat with fluoroquinolones. They'd mostly retained their resistance to the aminoglycosides. And this particular strain, 219, had also become resistant, highly resistant to fourth generation penicillins and also to carbapenems, so beta-lactam antibiotics, as you can see. It could be treated, luckily, with things like polymyxin and third generation cephalosporin still, although it had an intermediate susceptibility here, so indicating that it might be becoming resistant. So having shown that sort of phenotypically, we then went on to see what genes had these strains acquired in this particular sequence type, 308, over that 20 years. And so I'm just highlighting here the genes that had been were different between the 1997 isolates and the 2018 isolates. So both strains in the 2018 isolates had acquired this particular gene here, which is associated with fluoroquinolone resistance. And strain 218, which has got this very, very high resistance to fluoroquinolones, had also acquired this gene here, which actually makes it resistant to both fluoroquinolones, as you can see, and also to aminoglycosides, which may also be why it was highly resistant to something like gentamicin as well. This particular strain had also acquired lots and lots of new resistance genes for beta-lactams, as you can see here, which is probably why it was also highly resistant. Fortunately, neither of them had acquired genes for resistance to polymyxins, although some Pseudomonas are known to contain those. So, as you can see, bacteria can acquire resistance from the environment, and they acquire resistance genes from other bacteria or resistance genes that happen to be expelled by dying bacteria that they can then take up and use as well. But that's not the only way that they can become resistant. And so they can become resistant by mutating the genes that they already possess. So they don't need to acquire new genes. They can mutate the genes that they already have. And you can show this very easily in laboratory experiments that Pseudomonas can rapidly gain resistance to something like ciprofloxacin. And I'm using that as an example, but It could also be an aminoglycoside that we used here as well in these experiments. So I'll just take you through what you're going to see in these experiments. So what we do is in the laboratory, we take Pseudomonas, and we took this particular strain here, and we grew it in very low levels of antibiotics, so not enough to kill it or not enough to stop it growing. So low levels of antibiotics. And we grow that in one day, and then we take some cells out and we put it in fresh media containing that low level of antibiotics. The next day, so on and so forth, for at least 30 days. And we're passaging, we're growing the bacteria each day in fresh media containing low levels of antibiotics. And then we take those cells each day and we do what's called a minimum inhibitory concentration. So we're looking to see what the concentration is now to actually stop them growing. And so what we show here is a fold change. So this just means it's increasing its resistance. So I'll show you what happens with this particular strain over that 30 days. As you can see, by day 6, it's mutated itself to become more resistant, mutates again at day 7, mutates again at day 14, and mutates again at around about day 24. And at this stage, if we went on, we may have got some more mutations, but it's got about a 65-fold increase in its resistance, and it's become highly resistant to ciprofloxacin. So just by growing it in low levels, you can make these strains resistant. So this strain isn't actually a strain from the eye, and we can show that we can do exactly the same with a strain from the eye. In this case, it's a strain called 155. It looks slightly different, but again, by day 9, there's a mutation that makes it resistant. By day 13, there's another mutation. By day 21, another. By day 25, another. And at day 30, again, it's become 65 times more resistant. So we can Pseudomonas rapidly gains resistance just by mutating itself. We can show that, fortunately, if you remove the antibiotics now, they actually start to lose resistance. So I'll show you what we did here. So we did the same thing, and at day 32, we removed any antibiotic and then just grow them again each day. And as you can see, they can rapidly lose resistance, and that's because it takes energy for them to become resistant. And that's important for if you think about treatment. So you could, if a hospital, for example, has high levels of ciprofloxacin resistance, it could decide to remove that antibiotic from being used for a while, and then strains will slowly become more and more sensitive to ciprofloxacin, and then they could reintroduce it again. Just briefly on tolerance to antibiotics, there's another way that bacteria can become kind of resistant to antibiotics, although it's called tolerance in this case. So tolerance is the ability that doesn't have to be inherited for bacteria to survive transient exposure to high concentrations of antibiotics. And I'll also talk a little bit about biofilms as we go through this. There's different ways of testing tolerance. The one we use most commonly is either a ratio of the minimum bactericidal concentration compared to the minimum inhibitory concentration. And to be classified as tolerant, bacteria have to have a ratio greater than 32 or more, or this thing that's called the tolerance detection test. And what we do here is we just grow bacteria in the presence of an antibiotic soaked into a disc like this. And then when we grow them, the bacteria that are sensitive don't grow around that antibiotic. But then if you take the antibiotic disc off and you apply a disc this now containing a nutrient source, what we use is glucose, if they're tolerant, you can see that some strains that didn't grow in the presence of the antibiotic now start to grow. So you get some strains growing in this, what was an inhibitory zone. And so you get strains that have low level of tolerance, a few cells grow, medium level of tolerance, more cells grow, and high level of tolerance, you get lots and lots of cells growing when you take the antibiotic away and give it a nutrient supply. So again, looking at Pseudomonas strains, we look at tolerance from strains that have been isolated from eyes, and we can't find any evidence of tolerance when we look at this ratio. But if we do that TD test, we can actually show that many strains of Pseudomonas can become tolerant Indeed, as you can see here, this strain 181 became highly tolerant to ciprofloxacin. Tolerance is a problem because it is probably what causes many treatment failures. And it's known that treatment failure rates for ciprofloxacin are associated with installation of fewer numbers of drops and hence concentration of antibiotic on the first day of treatment. And that probably allows the cells to go into this tolerant state. And once antibiotics are taken out, they can reactivate and continue to cause the disease. The other problem with tolerance is that cells that are tolerant accumulate mutations, which then might lead to resistance. One other way that bacteria become tolerant is to produce biofilms. These are agglomerations of cells encased in a polymer matrix. And you can imagine these stuck to a contact lens, for example, and the bacteria produces polymers to basically protect themselves from things like antibiotics or indeed our host defense systems. So we've been looking at this in whether biofilms of Pseudomonas do make them tolerant or resistant to the effect of something like ciprofloxacin again. So we took a strain that was susceptible and we took a strain that was resistant. These were actually isogenic isolates, meaning that the only difference was that we'd made this susceptible strain resistant. So they were, other than that, genetically identical. So we produce biofilms and then we expose those biofilms to ciprofloxacin. And we expose them to half the minimum inhibitory concentration that was needed to kill the cells if they were in solution, the inhibitory concentration. And that means that if we expose the cells to this concentration in solution, 90% of cells die, 2 times that concentration or 4 times that concentration. So in biofilms, in order to get 90% death, you need 4 times the concentration of the antibiotic compared to what would be called a minimum inhibitory concentration if the cells were simply in solution. With the resistant strain now, that's for the susceptible strain. With the resistant strain, not surprisingly, half the MIC doesn't have any effect. 1 times the MIC doesn't have any effect. 2 times the MIC doesn't have any effect. And 4 times the MIC, in fact, doesn't have any effect. And so in a biofilm, it's basically impossible to kill these resistant cells when they're in a biofilm, even if you go up to 4 times the MIC, which actually would be probably too strong to be used therapeutically anyway. So the future for antibiotics looks somewhat grim because of the resistance that's occurring all around the world. And it's been predicted by 2050 that 10 million people per year will die of antibiotic resistance infections. And that's more deaths than anything combined other than cancer. And the WHO have nominated Pseudomonas aeruginosa as one of the priority pathogens for which new antibiotics are needed urgently. There's only been 70 new systemic antibiotics and 1 related biologic approved in America by the FDA since 2010. But these are all from old classes of antibiotic, and we know that they will, in that case, bacteria will develop resistance easily within 5 years, possibly within 2 years. So we believe that prevention is better than cure. So what we should be doing is telling people who wear contact lenses ways of reducing reducing their risk factors, so reducing the probability or the possibility of them getting microbial keratitis. So never sleep in contact lenses, of course. Wear daily disposable lenses. While that might not reduce the absolute risk of contact lens related microbial keratitis, if they do get it, they get less severe forms and they don't tend to lose more than 2 lines of vision. If you wear daily wear, the best thing to do is actually to dry your lens cases between use and regularly replace them each month. This reduces the risk by greater than 60% of you getting keratitis. And contact lens wearers should be used to use the same case that they get usually free when they buy a new multi-purpose disinfecting solution. because if you mix the multi-purpose disinfecting solution with a different case, that has an effect and reduces the effectiveness of this disinfecting solution. And anybody who wears lenses on a yearly replacement schedule, which I know is really rare these days, but some are still doing it, should be changed to monthly or fortnightly replacement schedules. But we've been developing antimicrobial contact lenses, and I'm going to finish the talk by just talking a little bit about some studies that we've been doing on antimicrobial lenses, because we believe if you wear antimicrobial lenses, you'll reduce the risk that you'll get viable bacteria stuck to those lenses, and therefore then they won't be able to colonize your eye and cause the infection. So this again is Pseudomonas aeruginosa, and we also look at some evidence with Staphylococcus aureus here. We use a little peptide that we call either melamine or a variation of this called MEL4. This basically disrupts the outer membrane of Pseudomonas and the cell wall of Staphylococcus and causes them to die. If we do that experiment, remember that experiment with ciprofloxacin, where it becomes increasingly resistant to ciprofloxacin? We do that exactly same experiment, but this time with melamine at sub-inhibitory concentrations. The bacteria never become resistant to this peptide called melamine, or indeed its mimic called MEL4. And there are also other good things. It's also very non-toxic to our cells. So this is a measure of toxicity. So this arrow is pointing to the concentration that's needed to kill Pseudomonas, and at 10 times that, if not 30 times that, basically this is there's no evidence that it bursts red blood cells, or it bursts red blood cells at a very low level. It would have to get up to 30% to be considered toxic. So it's got a very high therapeutic index, the ratio between activity to toxicity. We can attach it to a contact lens, so it's chemically bound and doesn't release. And we can show that those contact lenses then prevent the adhesion of bacteria. So this is the inhibition of adhesion. So we got about 2.5 logs inhibition. And we've put them through animal models of contact lens wear and safety, and phase 1 and phase 2 human trials. And we went into a trial at the Albert Prasad Eye Institute for a phase 3, looking at whether our antimicrobial contact lenses could reduce the incidence of microbially driven adverse events or infiltrative events. Basically, these are all caused by bacteria stuck to lenses and include things like microbial keratitis. During the 3-month period of people wearing the lenses while they slept in lenses for 24 hours a day, for a month, and then threw their lenses out and used another lens. So over 3 months. We had various other secondary objectives to make sure that the lenses were safe, that they retained activity, and they didn't affect what's normally present on the ocular surface. So I'll go through this, but we had 16 adverse events during the trial. We showed that the lenses that we made were antimicrobial before and during the trial, before the people were wearing them, and indeed afterwards. Whilst they wore the lenses, there was no difference in things like redness or indeed staining or palpebral roughness. You can see here that there's no difference between the antimicrobial lenses and the control lenses. They were also perfectly comfortable, no significant difference between the two different types of lenses, and it didn't change the bugs on the eye. We did have adverse events. We had 18 adverse events, and if we follow this one up here, these are the ones we're interested in. We had 9 corneal infiltrative events, 6 contact lens-induced acute red eyes, and 3 infiltrative keratitis. And when we looked at which lenses were associated with those, we found that we had a 69% reduction in corneal infiltrative events of the eyes that were wearing these MEL4 coated lenses. So we met the primary objective of the study, which was to show a greater or equal to 65% reduction in CIEs. So that was really good. We showed that if you make an antimicrobial contact lens, you can control the production of adverse events such as corneal infiltrative events, and if it was a big enough study, we predict also microbial keratitis events. What we did show was, interestingly, that the people the eyes that were wearing the MEL4 lenses, this is in orange here, seem to all have their adverse events right at the end of the study period. So during their time of wear, so at around about 13 days of wear. Whereas in the eyes that were wearing the control lenses, they sort of randomly happened much sooner than that. So we were interested to see why that was the case. We did another study where people wore lenses for 8 hours or 1 night, 3 nights or 6 nights. And we took those lenses out and see if they retained antimicrobial activity. And you can see by 6 nights of wear, for this particular strain of Pseudomonas and this particular strain of Staph aureus, it does change a little bit depending on the strains, but for these ones, they'd basically lost their antimicrobial activity by 6 nights of wear. And we thought that was the reason that we were getting this difference between when we got the adverse events with MEL4 and the adverse events with the control lenses. We thought that might be to do with proteins or lipids depositing on the surface of our antimicrobials and therefore covering up their activity. But indeed, for both proteins and lipids, the MEL4 lenses, the antimicrobial lenses, actually had less proteins and lipids on them, so that didn't seem to be the case. But what we did show was if we took our MEL4 coated lens, which you can see here has a low level of bugs attached, Pseudomonas aeruginosa in this case, compared to a normal lens, we took those lenses and digested them with a protease called trypsin. We lost all antimicrobial activity. So there was no antimicrobial activity left, and we think that's the reason. So we've then gone on to make mimics of our antimicrobial peptides. These are much cheaper to make, which is good, but also resistant to protease. And we've shown recently that particular types of these, with 3 different strains of Pseudomonas, actually we can't ever find a single live isolate of Pseudomonas if we coat lens with 2 of these, TM5 and TM18. So we're hoping now to take these into clinical trials and show, hopefully, that they produce an even better response than our MEL4 contact lenses. So I'll end there and thank all of these people who helped over the past, must be nearly 20 years we've been working on these antimicrobial lenses. And I'm very happy to take questions if there are any. Thanks.
Thank you, Prof, for that comprehensive talk. I think we do take microbial keratitis as, I think, one in so many people, we don't care about it, but actually we really need to look for it in terms of diagnosing it early and knowing that so many options are probably not yet available or still in, research practice. It's much more of an interest. The first question which came in, and now because of this AI being so famous, and AI is kind of the present and going to be also the future with us, not going to leave us very soon. So what are your thoughts on using this AI intelligence or artificial intelligence to identify and produce varieties of antibiotics? Any thoughts over it?
Yeah, we can definitely do that. And in fact, those peptide things that I was talking about that we were using to coat contact lenses, some people are using artificial intelligence to make better versions of those peptides as well. So certainly a hot area at the moment is using AI to tweak either old antibiotics to make them better or to find new antibiotics. Many people are doing that, and I think that could be hopefully a boost to the antibiotic industry.
That's right. Yeah. And I think one question which just came in directly to me is asking about what could be in for a clinician as a sign to know whether the bacteria is already resistant to the medication which probably was prescribed to a patient who has MK or any infiltrates. Anything you would look for?
Unfortunately, there's nothing clinically that'll tell you that the bacteria is resistant. So you're only so you either have to keep giving the antibiotic, and if they don't get better, it's probably a resistant organism. The best thing, though, is to do a scrape and send it to a microbiology lab and get it tested to see what it's sensitive and resistant to. So that it won't look different clinically. It'll maybe look a bit more severe because it'll last for longer. But initially, it won't look at all different clinically, unfortunately.
Right. So it's more like clinical decision making in terms of follow-ups. Is it getting better? Is there any
Yes.
what things you look for? And then based on that, you
might expect Pseudomonas keratitis to get better, to show signs certainly within a week, if you've got the right antibiotics and you're giving them at the right concentration and stuff. So if it's longer than that, you'd certainly presume that it was either a different bug or it was resistant to antibiotics.
Okay. And I think one question more is about the artificial tears. You did mention that there were some artificial tears which were called back due to the kind of putting in more of problems rather than solving it in easier terms. Any thoughts over what should be taken care while prescribing these artificial tears, especially to patients who have these keratitis or at a risk of keratitis?
So these artificial tears have been imported into the States and actually hadn't gone through the regulatory approval, the regulatory authority approval, I don't think, and had been shown during this outbreak to be actually contaminated with the Pseudomonas. So it's important probably to prescribe from reputable manufacturers that have shown that they've gone through the correct tests to be registered, I guess, through something like the FDA in the United States, or what we have in Australia called the Therapeutic Goods Administration. And there are various other things in different countries, obviously. So you would want to have a reputable producer.
Yeah. And any role of preservatives or things like that which we need to take into consideration, because now we have artificial tears which are preservative free. Would you prefer to look into that as well? Would preservative be something which would worsen the condition probably?
Yeah, that's a double-edged sword. Yes, so these particular artificial tears that caused this outbreak in the States were actually unpreserved. But as you say, preservatives can also cause damage to the ocular surface. So it's a bit of a double-edged sword. Single-use unpreserved is probably optimal, but that's not available everywhere.
That's right. Okay. And I think we'll take one last question here is, if you get microbial keratitis once or twice and it's treated with an antibiotic, are you more or less likely to get it again, assuming you don't change your risk habits? So anything on that?
Yeah, thanks, Donna, for the question. So interesting question. I don't think there's any good data about that, but if we think that these corneal infiltrative events, which are similar to microbial keratitis, certainly if people have a corneal infiltrative event once, they're more likely to get it a second time because they don't change their habits necessarily. But because the actual infection event is so rare, I don't think we've got any good data to suggest whether you'd get it again or not. I don't think many people get it twice. It's just a rare event.
Right. So I think as a clinician role, it's always good to counsel your patients that you need to be utmost careful because you are in the risk zone to make sure that probably doesn't happen or it doesn't worsen the condition. So I think the role of clinician plays a very important as well.
It does, and get them to and ask them about what risky things they might be doing. So get an idea from the history what they do. Do they nap in their lenses? Because even 1 hour nap in lenses can heighten your risk of getting keratitis. Are they using the right lens case if they're daily wear with the right solution? Are they throwing away the case and not keeping it? Some people seem to fall in love with their cases and keep them forever.
That's
So
right.
try and get the case off them and give them a new case. That would help to reduce the possibility of them getting it again.
All right. And I think one interesting question I just thought we'll take in. We did talk about stopping or giving a break in the antibiotic therapy, which might reduce the resistance. Do you think it's a good idea to substitute with artificial tears in between, or do something in between when we restart it back, or things like that? Or any thoughts on that?
So I think what I was trying to suggest was not to a single patient. So if a single patient has got an infection, and you're giving them ciprofloxacin, let's say, to treat that infection, if it's not getting better, you change that. You culture the bug and see what it's resistant to or sensitive to, and give a different antibiotic. So what I was suggesting, when you remove an antibiotic, it would be from kind of being prescribed generally in the hospital, let's say, and so the bugs in the environment of the hospital or outside start to become sensitive again. So for a patient, you shouldn't really stop antibiotic treatment. You should either you should basically try and find out if the bug is sensitive to a different antibiotic if you think the infection is lasting too long, and don't give artificial tears. Don't stop an antibiotic treatment. Give another antibiotic. Don't use artificial tears.
Great, thank you so much.
Sense.
Yeah. All right, great. So thank you, Prof, so much for that comprehensive talk, and also giving us some insights in terms of the questions asked today.
Pleasure.
And we appreciate spending your Sunday evening already now with us.
No, thanks. A pleasure. Thank you very much.
We do have session planned over the next week. Till then, take care, be safe, and hope to see you during the next session. Bye-bye.
Bye. Bye-bye.
Bye, Prof. Thank you.